Hello. Am I audible? Yes. I'm sorry. I'm sorry. My computer is playing up. My laptop is playing up some tricks because of the rain and disturbed internet. So I'm logging into my mobile. I just hope we can manage something. Okay. Am I visible as well? Okay. Thank you very much. And can you? Yes. 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 Okay. Yes. Okay. All right. All right. Um, I think we have a little bit time left. In the meantime, just a general conversation. Dr. Amrita Pasak, good morning. Um, I hope I'm audible to you. And
Yes.
formally,
Can you hear me?
yes, I can. Thank you very much. We'd like to welcome you to our college, and we're looking forward to this so much. Um, just that we have a little disturbance with the network because of heavy rain. and we'll be starting in a few
Oh,
minutes. And
sure.
yes, just in a few minutes we'll be starting, and just wait until the correct time. And yes, and we are all very glad to have you amongst us today. And to Dr. DC Roy, I hope you are also there, Dr. DC Roy. But in a few minutes we can start. I'm also trying to log in through my laptop, but as I saying, getting ready to open right now. I'm still on my phone. I can see that a lot of people are joining us, and my apologies to everyone because of this network and the rain. I'm having a little difficulty joining through my computer. I hope my phone will stay still. So uh, yes, Yoshna, am I audible now? I do have my headphone on. I do have my headphone on, so I'm audible, right? Okay. So I think it's time, if the departments are ready to go, I will start the webinar. And I will try to log in from the other, my computer later on. I think it's time for us to begin. Is it okay to begin? Is the department ready? Is Dr. DCY ready? Dr. DCY, are you there? I I am not getting any feedback from the teachers there, from the departmental teachers. Dr. DCY, are you ready? Uh-huh. Mhm. There is still some disturbance, I guess. But it's 12, so do you think I should start? It's L. Should be okay to start. Yes. Dr. J.C. Roy, can I get a feedback from you, Dr. J.C. Roy? If I can just get a go ahead from Dr. J.C. Roy, I think I can start the webinar.
Yes, Josana, I am here.
Yes. Sir, can we start the webinar now? Is it okay? So, good afternoon, everyone. On behalf of Kalimpong College and the departments of Physics and Mathematics at Kalimpong College, I welcome everyone to this first international webinar hosted by Kalimpong College. This is actually the 11th webinar in the series that we are hosting during the COVID times. But today we are extremely happy because this is our first international webinar and we have very eminent resource people speaking to us today. And we've been looking forward to this. We've been looking forward to this for a long time. And so despite the bad weather, we are really interested and we are excited about participating in this webinar. And our principal could not be here with us in the morning session because he had to go to Darjeeling to meet with the administrators of our regional government. So they are having a meeting there, so we could be present. But for today's webinar in the morning, let me welcome everyone, especially our resource person, Dr. Amrita Basak, and everybody who is present here. And very warm welcome to everyone. And for a formal welcome to the webinar, I hand over the proceedings to Dr. D.C. Roy, who is the head of the Department of Economics in our college. So Dr. D.C. Roy, over to you. Dr. D.C. Roy?
Yes, am I audible?
Yes, yes, sir.
Am I audible?
Yes, sir.
Okay.
For everyone, let me inform everyone. Please kindly mute your mics and switch off your videos so that we can have a smooth, relay of the program. Otherwise, we will be disturbed. So kindly switch off your mics and your videos, and please do not present. Doctor, over to you, Dr. D.C. Roy.
Okay. On behalf of Kalimpong College, let me welcome all the three distinguished speakers and the participants all over the globe at this international webinar, COVID-19, Quest for Some Solution. This webinar has been organized by the Physical and Mathematical Departments, Kalimpong College. Today, our principal sir had to go to Darjeeling to attend all Hill College principals meeting with the chairman GTA. Although he will not be able to address these gatherings in this first technical session, but I hope he will be available in the second technical session, which will be starting at 5 p.m. Pandemic had caused pandemic because of this COVID-19 had made us more tensed and stressed. But there are some positive aspects as well. In fact, it all depends on the attitude of the person who assesses the situation. Why I am saying so, that I like to discuss with the help of an example. Let me take a pot of 10 liters where there is 5 liters of water. Now, if I ask a person to describe the situation, somebody may say there is 5 liters of water. The other person may say there is 5 empty space in the pot. Apparently, we may say that the first person has a positive attitude while the second person has the negative attitude. But to me, the second person is more positive than the first person. Why I am saying so? Because the second person may have the intention or target to fill the remaining vacant 5 liter with the water. This positive attitude will enforce him to fill the water in the vacant space. Similarly, COVID-19 has taught us many more new things and also changed the very lifestyle of human beings. We are commonly being using new terminologies like pandemic, lockdown, unlock, social distancing, then containment zone, work from home, and lastly, this webinar. Now, in this changed situation, we are more habituated with the webinar than the earlier seminar. Seminar has no more made possible because of the restrictions caused by COVID-19, and webinar has been very popular nowadays. This webinar has so many positive aspects as well, because we could overcome the distance and can hear the speaker from any part of the globe. During this present pandemic, we could organize 10 webinars in our college. This is the 11th one, but this is the first international one. In today's webinar, we had 2 eminent speakers from USA and 1 from New Delhi, and there are good number of participants from all over the globe. We are receiving mails from the participants in all over the globe stating their inability in registering through the Google Meet. We are taking care of and sending the link to join us either through Google Meet or through the YouTube channel. Although the webinar has organized by the physical and mathematical departments, but our participants are from the different disciplines, maybe from the science background or from the humanities background without much of the technical knowledge about the scientific terminologies. So I would request and hope that the speaker should not mind to compromise somewhere in the delivery to take care of all the multidisciplinary participants. Now, I'd like to welcome Dr. Amrita Bosak, faculty member of Department of Mathematical Engineering, Pennsylvania State University, USA. I don't like to make her waiting much. It is already 2:30 in USA. When all her colleagues are taking rest or sleeping, Dr. Bosak is waiting to deliver her speech for us. Thank you, Dr. Bosak, for accepting our invitation, and hope to meet you personally sometime, somewhere, and I would be very happy if you could make some time to visit our college. With the permission of the principal, sir, now I like to declare today's webinar open for discussion. I request Anukampa ma'am to proceed with the proceedings of the first session. Thank you all and hope a great success of today's webinar. Over to Anukampa ma'am.
Thank you, Dr. D.C. Roy. I hope I'm audible once again. If Yoshna could give me feedback. I hope I'm audible. Yes. Okay. So, ladies and gentlemen who are present over here, all the participants, it is a great pleasure for me to introduce to you Dr. Amrita Bosak. You can see her introduction on the screen there, and I will be reading out for those who are having a difficulty. So, yes, have in our midst Dr. Amrita Bosak, Faculty, Department of Mechanical Engineering, Pennsylvania State University. She's also associate in the Institute for Computational and Data Sciences, Pennsylvania State affiliate. Materials Research Institute, Pennsylvania State. She is also graduate faculty, Mechanical Engineering. She is also graduate faculty for Additive Manufacturing and Design. She is the Director of Materials and Manufacturing Innovation Laboratory. She is the Director of Metallography and Materials Characterization Laboratory. She is the Co-Director, Electromechanical Systems Laboratory, all in Pennsylvania State. And we are really glad to have her with us today. She is a great resource person for us, in charge of and in all of this responsible work at the Pennsylvania State. So in discussion with us today is Dr. Amrita Basak, and she will be talking to us in the topic in situ biomechanical failure, evaluation of metallic implants in surrogate body fluids. Ladies and gentlemen, please welcome Dr. Amrita Basak. Dr. Basak, over to you.
Thank you so much for the introduction. And can you guys hear me? I hope.
Yes.
Great. So let me just share my presentation. So are you seeing my screen? Hello, are you seeing my screen? And the presentation? Okay. Okay, just give me a moment. Bye. How about now? Did you see something? Okay. All right. How about now? Okay. So I know the topic of the your webinar series is something on COVID, but I thought maybe this particular aspect of metallic implant is also going to be interesting to all of you, because this is sort of related to all of us, and this is something probably all of us have encountered at some point in our life, or in our relatives' life, or something like that. So my contact information is here. Please feel free to reach out in any case, if you have any questions for me. So the overall, the way I arranged my presentation today is basically I'll talk a bit about myself, how, what was the trajectory of my career so far. Then I would talk about the kind of research I do at Penn State. And finally, then I'll spend majority of my time actually talking about, metallic implants. So I was actually, basically I was born very near to Kalimpong. Actually, I was born near, in Coach Bihar. And then I spent majority of my life, high school and everything at Raiganj. After that, I moved to Calcutta, where I did my undergraduate at Jadavpur in chemical. And then actually I moved to IIT Kanpur, Indian Institute of Technology Kanpur at Kanpur basically, and I did my master's in chemical. And after this time, I actually got a position at General Electric in their aerospace division. So I was a lead engineer for them for about 6 years. And then eventually, after 6 years of sort of working, I decided to pursue a PhD. So then, of course, I flew from Bangalore to US, East Coast of US. And I think I was fortunate enough to get an admit at Georgia Tech, So Georgia Tech is considered to be one of the like top mechanical school as such in the US. And as opposed to some of the traditional, traditional educational thing that happened in India, in the US, the education system is very open in the sense that you can pretty much pick any subject that you want to study. It just depends on what your interests are. And I ended up actually studying a bunch of different things because initially I was not sure what I want to do with my life. So basically, I graduated with a degree in mechanical, but at the same time, I actually studied like aero and math and material science and all of it. So I graduated with a PhD in 2017, and then actually traveled like from the east part of the US to the west part of the US. And as Dr. BC Roy mentioned, that these days, because of the COVID situation, I think everybody is talking about social distancing and all of that, and everybody is also talking about PPE. So I ended up working in Intel. Intel Corporation is the one. Probably all your cell phones and laptops are all using Intel chips. So if you are working in a fab, I used to work in the fab. You pretty much wear PPE all the time because inside the fab, the environment has to be so pure. Your sweat can actually destroy the chip. So your sweat is like a big bad thing. So that's why if you see inside the fab, everybody walks like a zombie. So I spent about a year working for Intel, and then eventually I again traveled from the west to east. I am very close to New York. Penn State is actually extremely close to New York, and I think all of you have heard about Niagara. So Niagara is just like 3 hours drive from my place. So it's a nice place to live as such. And I joined I joined Penn State last spring, so January of 2019. And it's almost like 1 year, sort of 9 months for me. So basically, Penn State is an really beautiful place, I would say. So we actually have sort of like all type of research facilities that we can think of. We also are a very heavily focused on research. So you can see this chart, and in 2020, the current year, the research expenditure was over 1 billion a year. So we actually spend a lot of money in research, which actually gives us a lot of facilities. So basically, look, this is our Material Science Institute, actually one of the affiliation that I have. There are certain other fun facts. Basically, we have a stadium, and you can see like a full packed stadium. So if this was not a COVID season, it would have been full packed during the weekend games. We also have flying clubs in case somebody is interested in flying. We have a special like bakery for us, and creamery and bakery, so you can enjoy a lot of ice creams. And finally, I don't know if you are aware of fall color. Fall is extremely awesome at Penn State. So overall, this is a pretty nice place to be in as such, and do research, I would say. So my current research actually encompasses different things. So my major research is in actually manufacturing, but I also try to do sort of like, computational modeling kind of thing, and all the things that are in italics on this chart, like machine learning. This is something I have started learning after coming to Penn State. I didn't really work on it before, but after coming to Penn State, I thought it's probably the right time I should start learning something that I haven't done before. And I do a lot of testing. So basically, when you manufacture a part, manufacturing is not the end of the story. And I can give you a very simple example. Suppose your objective is to manufacture like a teapot. It can be as simple thing as teapot. But then if the teapot, you put it on a stove and the teapot just bursts, it did not serve the purpose. So basically, you need to make sure that teapot is good enough that you can actually make your tea, and it doesn't fail during the manufacturing or during the processing steps. I mostly work with metals that are typically used in, say, aircraft engine, or rocket engine, or power plants, like the plants that generate electricity for you. But I also started to work on something like ceramics and polymeric stuff. Uh, just again, out of my own interest in learning other material systems. So these are some of the like pictures of the equipment that I have in my lab. I wanted to get good pictures, but unfortunately, I couldn't make it to my lab. The lab where I am. I was working today. So yeah, this is all I had from my previous presentation. So anyway, so before I actually start sharing, majority of all the work is done by my students, and I am extremely fortunate to work with some of the, I would say, some of the smartest student. I was not a smart one when I was a student as such, but my students are extremely smart. So I lead a group of, research scientists, PhD students, master students, and undergraduate students. And they are pretty much the one who have done all the work for me. So it's a fun thing that they do all the work, but I get to talk, right? Yeah, so before I start, I should thank them because the work belongs to them actually. So let's dive in. So implants are some of the things which are, it's used everywhere in the human body whenever a certain organ or certain part of the body fails. For example, I think all of you are aware that there are dental implants. So suppose if your gum is eroding, if you have a tooth problem or a teeth problem, so there are certain implants that are being used in your mouth. Similarly, if you have a broken bone, if somebody has a broken bone, they actually use some sort of like a broken, bone plate to make sure that the bone heals. There are hip or artificial joint implants. For example, as we age, our bones actually start to become porous, and it actually starts to lose its strength. So that means, there may be times when the joints are actually not working properly. Suppose your knee joint, your hip joint, and all of that. So we need something. My dad had a pacemaker all his life. So he was fitted with a pacemaker, I think, when I was doing my master's. So pacemaker is also like an implant. Similarly, stent is another implant which is used in the heart. When the heart, the capillaries are actually, they reduce in diameter because of, say, cholesterol deposition and all of that. So there are different type of implants that are used in our body. And most of them, as you can see, they are called alloy, which means they are sort of like metallic material. And I think all of you would be probably familiar with this name, stainless steel. So stainless steel is used, but one of the very common alloy that is something that I have highlighted here is something called a Ti-6-4. So basically titanium, aluminum, vanadium. This is a very famous alloy, which has been used for fabricating metallic implants, since this implant domain came into existence. So as you can see, the first problem is you have to pick a material for your to fit inside your body, and you cannot pick any material. For example, if you pick a material which is, say, which produces rust, that means you don't want that inside your body, right? Because it is going to produce rust when it is inside, and it is just going to fiddle around. You don't want that. The next thing is, okay, I picked a material, but then the question is, how am I going to manufacture it? So the manufacturing comes into the picture. That I have my material now, but I need to manufacture it somehow. And the third part is, which is the most critical part, that is actually testing. Because finally, you want to put all these components inside, a person's body. And you need to make sure that you can do all possible testing that you can potentially think of, so that it is not harmful when it is being planted in someone's body. Because if it produces something which is not good for your health, then it is actually going to be harmful to the to our physical system, right? So it is going to produce something which we won't like. So manufacturing, material, and testing, all these things are sort of interrelated with each other. And in this particular talk, I am not going to be talking, talking about material, because material, what type of material design I have to do, that could itself be a big talk. And I sort of like, I'm just trying to just focus on manufacturing and testing part. So the majority of, or the next part of the talk, I'll just say that, okay, you know what, let us pick this alloy. Let us pick titanium 6Al vanadium, this particular alloy. Okay. So this is, as I said, this is a very famous alloy, and very famous means it has been used for many different applications. And the reason being, first of all, it's extremely strong, and it has got extremely, it is really corrosion resistant. Corrosion resistant means, suppose if you take a piece of, steel, and if you take a piece of, say, Ti-6-4, you put both of them in the open atmosphere, the steel, after some time, probably there would be some rusting, but Ti-6-4 will be like immaculate. There are not going to be any rustings on Ti-6-4 because it's extremely corrosion resistant. This has been discovered sometime around 1950s, when people were doing armor design. So basically, when our military goes to the war front, that they all wear certain armor so that they can be protected. So that is how this alloy came into picture. And it was discovered at Army Research Laboratory at US. And that is how after that this came into, like, there has been a lot of application where we use Ti-6-4. Again, this is sort of the chemistry of it. So you can see the majority of the component is something aluminum. So I think all of you are aware of this name, aluminum. Vanadium is a bit of exotic element. Titanium is also a bit of exotic element. We don't really see titanium and vanadium a lot in our real life, but these are also metals. Just like aluminum, titanium, and vanadium, this is also metal. So basically, this particular alloy is like a mixture of metals. You can say mixture of different elemental metallic component. And a fun fact. So the fun fact is, I hope that all of you probably have traveled by aircraft at some point in your life. So if you see, this is the engine that hangs beneath your wing. So when you climb the aircraft next time, you would see this stuff which is hanging beneath the wing. That is the engine which actually powers, or which actually produces thrust so that the aircraft actually flies. And the engine looks pretty nice because it is being covered. But when you open up the covering, you would see that this is like a junk, it's like there are a lot of wearing tubes and all of that inside the engine. So in order to cover it up and make it look pretty, they just use this casing. And if you again, try to take a look at it, there is a certain stage inside this engine, which is called compressor. Basically, this is the place where you compress the air. And, the fun fact is, the exact same material is used in compressor blade as well. So if you have an implant, or if you know somebody who has an implant, he or she is actually sharing the same material with an aircraft engine. This material is so versatile. So basically now then going to the topic of this, implant. So why do we need an implant? So for example, this is a case of, say, severe arthritis, where the patient or the person is actually having a, his or her joint. The joint actually degraded over a period of time. So you can see one, this side of the bone structure is pretty nice, but this side of the bone structure is, all porous, and it is actually, corroded. It actually, it had stopped functioning. And if something like that happens, what would happen is your hip portion or the leg portion is just going to be swollen, and pretty much the patient cannot walk. So the solution is typically you actually section, or you chop off some portion of this part, and you chop off some portion of this part, and in this particular part you actually put a metal piece. So now this metal piece, which is, some portion is inside the femur and some portion is inside this particular bone, this actually does the function of the joint that you originally had. So basically think about your leg or think about your knee. It can move, from right to left or, back to front, from side to side, all of that. So that means this joint has to be something called a ball joint or ball bearing. So there is a ball and there is a bearing and it can move around. So the same kind of like, front to back or side to side or, pitch roll, this kind of movement you can achieve with this metallic piece. That's what this particular implant is doing. So every implant has its own functionality, but it doesn't really matter the functionality, as such, but also the material, what material you are using, how you are designing that part, it matters, right? Depending on where you are going to put this implant, you have to figure out what type of design you need. So by the look of it, so if you see the implant, this looks like a really nice piece, right? Oh yeah, I mean, I can make it probably, this doesn't look very complicated. This is like a ball and I have a sort of like a cylindrical object, conical object, and I can probably make it, right? But the problem starts with the fact that if you look at the picture of a bone, healthy bone, it's actually porous. Your bone has a bunch of pores in it, and as we are gonna get old, this actually becomes a bit more porous, and that is why, at our old age we actually start to lose strength of our, we cannot walk for a long time, we cannot climb the mountain, all of that happens. But healthy bone, even if it is healthy, it actually has a lot of pores in it. Bone is an extremely porous substance. So the problem now is, originally you had something which was porous, and now you are putting like a solid metal piece inside your bone. And it has been shown by the researchers that instead of having a solid, this implant, if you can make a porous implant wherein, your implant will also have this kind of pores inside the, geometry, you are actually going to have a better bond, better connection between the bone, so between this part and the implant. So instead of a solid part, if you have a porous part, these two structures are going to sort of like connect with each other in a more appropriate way. However, if you see or if you think about it, all of us, we have different body shapes. Our heights are different, our bone structures are different. The way my bone probably, the way somebody's bone is structured, it is very different from somebody else's bone. So it is actually telling you, if you have a standard size implant, it is equivalent of saying that when you go to a market, you can buy only one size shirt, and everybody has to fit that shirt. Doesn't matter whether the person is, whether the person has like, same physique, everyone has to fit the same dimensional shirt, and which may not be the right thing to do, because all of us, all of our body structures are different. And this is one of the reasons. What happens is, post surgery, after the surgery, if this structure is not appropriately sized to the person, to the person's, bone structure or something, post surgery recovery or, physiotherapy becomes extremely difficult, because there are like different sizes in your body, and how the heck the body can adjust to it. So now the problem starts. Actually, now you start to see that, okay, just manufacturing it is not sufficient. I need to make it fit to my body, or I need to make it fit to the patient's body. And according to his or her structure, we have to now design this part and, of course, manufacture it. So now the problem lies with the fact that how do you print metallic foams? This actually has a fancy name. Porous structures, porous metallic structures are called metallic foams. So foam, if you see foam actually has a lot of pores. So similarly, if I want to make a structure which is made of metal, but it should have a lot of pores in it, I'm going to call it a metallic foam. Okay. There is a book on it. So typically, in a graduate school, sometime in a design school, we actually teach a course on it. So that means I am actually not going to go into a lot of details as to how we design or how we fabricate. Rather, I'm just going to give you an overview of some of the issues, with the process. So basically, there is a very traditional method of manufacturing these structures, and I think all of you are familiar with it some way or the other, because I think when I was growing up, there used to be this plaster of Paris, structures in our house, and it used to be sold in West Bengal quite a bit. So we all used to have those plaster of Paris, idols of different gods and everything available to us. So investment casting is like a 5,000 year old process. Egyptians actually started it, and the theory is very simple. So basically, if I want to make this part, suppose this is the object I want to make. What I am going to start with is I am going to make a mold. So I am going to surround this. I am going to make a mold so that the inside I have exactly this part, but a hollow part, and then I am going to pour metal in it. So if I pour metal in it, what will happen is, since I have the hollow part here, so the metal is going to fill that hollow part, and eventually I am going to break this outer casting, outer layer, and I am going to get my part. So investment casting is something wherein you make a mold, you pour the metal, and you get the part. And as I said, it is very old process. Egyptians started it. Of course, those days the process used to be very, how do I say it, very rudimentary, and now it has become extremely sophisticated. So with time everything becomes sophisticated. So this process has also become sophisticated. So again, I'm not going to go into details, but there are like different processes then by which, using investment casting. So if you make a mold, and if you follow this casting process, you should be able to make something called a, metallic foam structure. So this kind of structure you can make. It's possible. So the problem is, every time you want to build a new part, every time you have to make a new mold. I want to make a part for somebody, I have to make a mold. I want to make the same hip joint part for somebody else, I have to make a new mold now. And for every new part, the entire this manufacturing process needs to be optimized. So how fast I am going to pour my metal, what should be the temperature of the metal, all of that need to be optimized for every single part that you make. Every single design that you make, you have to do this. Now that actually brings to that actually is a huge challenge, because it's a problem. Because as I said, our body types are different, patients are, their bone structures are different. Now if I have to make a mold, and if I have to optimize my entire manufacturing process for every single patient that is available there, it would become so expensive that no one would be able to afford it. And that is why currently there is no patient specific implant. You basically have this one size shirt or one size implant. There are some flexibilities, there is a screw here, so basically you can rotate it and you can adjust some length. However, it doesn't give you a lot of flexibility. So basically, the conclusion is that everybody's size, shape, all of that is different. As I showed you in the picture, the bones are actually porous, and this how much pore or how much void you are going to have, that is also different. Your bone structure is not going to match mine. We have totally different structures. So this means patient specific implant is very expensive. You cannot develop patient specific implant. Excuse me, is there a question? Okay. So patient-specific implant is very expensive, and currently we don't do it actually. So then what is the solution? So I know that I cannot do that casting process. So what is going to be the solution? Is somebody's microphone, or can everybody put their mic on mute? I am hearing some sort of like a background noise. Thank you very much. So what is the other option? So back in 1980s, a new manufacturing process actually came into existence. It's called 3D printing, and it's also called additive manufacturing. And it became extremely popular because of the fact that this particular process is like a mold free process. Now you don't need to make anything to make a new part. What you need to do is, suppose you have an object, so you actually slice the object into multiple layers. So there are, suppose this is the object. Yes. Is
Ma'am,
there
you
a
can
question?
no, ma'am. You can continue. The question session will be at the end, ma'am.
Okay, no problem. Thank you. This is the object. Suppose you want to make suppose, and then you slice it up into different layers. So basically, 1, 2, 3, 4, how many layers I want. And then you have this printer. It's like the exact same printer that you have probably at your office or something. It's like a printer. So your home printer, it actually prints 2D because it's a paper. That's where it prints. The 3D printing actually happens along the Z direction or along 3-dimensional space. So that means you can build a part in layers. So the process is so simple in its nature that it became hugely popular starting in around 1984s. And nowadays, there are extremely good structures that you can make with 3D printing because, look at this process. We don't need to make a mold. We don't need to make that mold and then break it to get my part. All those things are not required. It's not at all necessary. And then what do you typically do? So for example, I want to make this structure. So sometimes if you see, your to make sure that your teeth is appropriately shaped, it is actually being supported by something called some other structures. So basically, somebody can take a scan of your mouth. So when you scan your mouth, you actually get exactly the kind of dimension your teeth has. And then you just feed this design to a 3D printer. So this is like a schematic of the 3D printer. And this is like the design, like you have the design in your computer. You feed the design to the printer and the printer actually prints it. Exactly the shape of your teeth structure or something, it would print. And then you can actually, fit it in your mouth and figure out whether it fits properly and all of that. So it became extremely simple. And with that, now what happens is that means, 3D printing can actually help us making those structures or making those implants, which would be actually customized for the patient. If the patient wants long implant, we can make it. If the patient wants short implant, or patient, it's not want, if he or she needs whatever implant type he or she needs, we can make it. And this was actually a very popular case study, which I thought I would share with you. So back in this Spain, there was a person who actually lost his rib because of cancer. So, that person's entire, top 3 ribs, actually 4 ribs, both side, it had to be removed because of cancer. And what the manufacturer or the doctor and the surgeons, they did was, they actually did like a patient specific design that, for this patient, I need this kind of metallic structure, which is not heavy, but at the same time, it would be able to hold his rib structure properly. And then they printed it and then they fitted it. And the patient actually, he or she is doing fine. And if you imagine, if I had to make this same structure using all those mold and investment casting or all of that, probably it would have taken so much of time, the patient probably would have died even before we can make the part, because that process is so long. So this is how you can see that, this new technology, which is 3D printing, it is actually able to now make things which are not possible using any of the traditional manufacturing processes. For example, again, these are some of the metallic foams, as I said, like metallic stuff. So all of these are metals, but you can see it has pores inside it. And these are some of the things you can possibly never make, with such complexity using investment cast or that mold process. And even if you can make, it is going to take so long that, after you achieve in making the part, probably it is not going to be relevant anymore. Just like the patient case, it would have taken so long, by the time probably the patient had died because it took so long. So this process came out to be really useful, and what now I try to do in my lab is basically try to make these structures, and because now it is possible actually to make patient specific implant, although we have to do a lot of optimization, because this manufacturing process is relatively new. It just came into existence in 1980s. And if you understand, the technology development actually takes quite a bit of time. 20, 30, 40 years is actually not a big time in terms of technology maturation. Sometimes it actually can take longer duration of time. So we still have to do a lot of work in terms of optimizing our printer, optimizing our material and all of that, because there are some materials which are actually easily, printed. We can print them very easily, but there are some materials which are really hard to print. So the materials which are really hard to print, our objective is, can we find out a substitute material, and of course, all the time we print something, we have to go for qualification. That means we have to actually test it to make sure that it is performing the way we want it to perform, right? It cannot be just, we don't want to print fancy items just because it looks fancy. It has to work, right? If a certain object doesn't work, doesn't matter how fancy it looks, it is actually not useful to us. It's useless. It has to work. It has to function. Then only it is useful. Otherwise, pretty stuff doesn't have much value in engineering, right? We don't want stuff to be just pretty. They have to be functional, right? So then actually the next part, as I said, we are pretty much sure, like, we actually at Penn State, I didn't mention that we also have a medical school here. So Penn State also has a health sort of department, and between College of Engineering, I am in College of Engineering. So between College of Engineering and our medical institute, there is actually a lot of collaboration that happens. Basically, I am not a medical person, and I would tell you a small story about me, that I have a brother, and my mother actually wanted one of us to become a doctor. So these days, and eventually neither my brother nor me, of course, we became a doctor. Both of us are actually engineers. So with these days, I joke to my mom saying that, oh no, you know what, this is the closest I can become to a doctor, that I am making, parts which the doctors can use. So in any case, we know we can print them, and we work a lot. I mean, I work a lot with the medical personnel as such, trying to find out what should be the material, how should the structure be, and all of that. So we know we can print stuff. So the next step is actually testing. You need to now test. It shouldn't happen that you put the implant in someone's body and the implant just fails. And there is a story again, I don't know whether you are aware. The first pacemaker that came into existence in 1958. So in 1958, there was the first operation, or the first surgery happened for pacemaker. And those days, the pacemaker quality used to be so bad. It was terrible, because, the battery technology was not good. All the pacemaker actually runs on battery. So that's why you see an electrode here. So all the, because it has to, function. So there is no electrical supply in your pacemaker. That means it is actually running on a battery. And the battery used to be, the technology for the battery development was not that good. So after implanting, or after planting the pacemaker in the patient's body, within 3 hours, the pacemaker actually failed. So they had to open up his heart again, not heart, like open up his pacemaker region again, and implant a new pacemaker again. It was 1958. It is just like, 60, some 80 years, not like, a long time. And that particular guy, in his entire lifetime, he actually had 26 pacemaker replacement operation, because the pacemakers, again, used to be so poor quality. And nowadays, you can imagine, like I said, right, my dad had a pacemaker, and it functioned for 10 years. Like 10 years, you shouldn't be worried about it. And I think nowadays it actually can run till 15, 20 years. So eventually the person or the patient, he actually outlived the doctor who did the surgery and the engineer who made the pacemaker. So that was the fun fact about pacemaker. You can actually look into the Wikipedia page, and there was a nice story about it. So in any case, after you manufacture something, after you have some material, now you have to test it. You have to test it so that it doesn't fail inside the patient's body, right? It shouldn't break, it shouldn't malfunction. So there are many different testing, many different testing method. And again, my objective of this presentation is just to give you guys some idea about how we design stuff. So I am not going to talk about fatigue, torsion, compression, and combine those kind of loading. I would only talk about something which is very simple to understand, and it's called tensile load. So tensile loading is something I'll talk about. Although I am more interested in actually, fatigue, and I am more interested in this torsion and the combined load. But again, for the benefit of, benefit of the presentation, and of course, I'm limited by the time, so I'm not going to talk about these ones. I'll just talk about the tensile one. So what happens in a tensile load? Again, I know I am probably talking to a group of people who are probably not familiar with the mechanical testing aspect, but I'll try to explain it as simple as I can. So basically, tensile load, what happens is, suppose you have a specimen, suppose you have a metallic, this is a rod, this is a rod of certain size, and what you do is you actually apply, you actually apply load. So there is a load here, so you apply force this direction and force this direction. So as you apply load, what would happen is you keep on applying load. At one point, since you can see this is the thinnest section and this is the thickest section, so the thinnest section would start becoming even thinner. So something that happens when you stretch a rubber band. So when you stretch a rubber band, if you do it next time, you would see the rubber band would start actually thinning at the center of at the center of the band. And eventually, if you put a lot of force in the rubber band, at one point, it is going to fracture. It is going to just break. It is going to tear apart. So this is something called a tensile load, because you are actually subjecting your material to something called tension. So this is like a tension situation. So this is this direction and this direction. You are subjecting your material to tension. And suppose I have made an implant, so I can actually take different, I cannot potentially, do the entire testing of the big implant, because it is going to be like, it is gonna take a long time. So for example, when you go to the market and you actually try to buy rice, you do not inspect the entire box of rice or entire this, dabba of rice, right? You just sample it out. You just take a small sample out of the rice, sack, and you just inspect whether the rice looks okay to you. Similarly, if you have a metal piece like that, you just take maybe 1, 2, 3 different specimens from somewhere and try to see whether it looks fine. So basically now, if you do this testing, load testing, as you can see, as I keep on increasing the load, this particular region is going to be elongated and elongated, just like a rubber band. As you keep on stretching, the rubber band keeps on getting, longer in its length, and eventually it just tears apart. So this is also going to happen. And the nature of most of the metal is something like it increases sort of like linearly. So as you can see, it is like a straight line, and eventually it goes through some other type of phenomena like plastic strain. Again, I'm not going to talk a lot about it. However, for the sake of all our manufactured implant, we want to operate somewhere here. We want to operate in this linear region. Basically, this is the region where if I am operating this specimen, I know that my implant is going to be safe. This is like the safe region. So I want to operate always here. I really don't want to go beyond this envelope. So basically, then there are different tensile testing setup. I have one of them in my lab. So you just put this metal piece in the equipment, and you just have a load. So you apply now the this tension load, and eventually you can plot it out and you can figure out where it is actually failing, which is okay. You can figure out where it is failing. But the question is, can we do better? And if you ask me why do we need to do better, the reason is I have now a metallic foam. If I had a metal piece which looks so smooth, my life is actually easy. But since I have a foam now which looks something like that, I want to understand exactly where it is failing, exactly which location it fails. Because it may be possible it is actually failing something, somewhere inside of the specimen, but I cannot see it because it's inside. So how do I know how it is failing when things are, when the failure is happening inside of it? Then of course, the next question is, how do I assess how this particular implants are going to fail in the presence of electrolyte? Electrolyte is something because your body environment is actually not that good for implant. Why? Because your blood has all the different type of electrolytes and salts in it, sodium, potassium, and all of that. And more importantly, it has dissolved oxygen, because we need to breathe, right? Our body and blood and everything, it carries oxygen with it. And if you recall, oxygen is very bad for all the metal because it actually oxides. So iron becomes iron oxide. Similarly, titanium may become titanium oxide. So oxygen is bad for metals because it produces oxides in it. So the question is, first of all, can I know how this is going to fail? Can I see inside? The second question is, how do I now assess this failure phenomena in the presence of like electrolytes? Is it going to be okay? Does it make any difference? Or is it going to be like bad? Is it good? Is it bad? Is it neutral? We don't know, and we have to find it out. So the major then problem is we would like to see the interior of the specimen. So basically, I'll give you a metal piece, and the question would be, tell me what is inside. What is inside of it? But then, how do we do it? How do we see inside of a metal? So there is a very good technique, and again, I normally boast about it because my graduate school, Georgia Tech, again, Georgia Tech was like top I think second school. But we don't have a CT there. It's called something like X-ray computed tomography. And at Penn State, we actually have 2 of them. And as I said, I am extremely proud about that we have 2 CT stages at Penn State. So what does a CT do? And I think, I don't know whether probably all of you have heard MRI, right? Typically, when somebody goes to MRI, MRI means, scanning of the body. So it's the same logic. So basically you have an X-ray source. There is this X-ray source and there is this X-ray detector, and you put your metal piece in between, and it is being put on a stage which rotates. So now as you rotate the stage, since you have the X-ray, and since the X-ray is, X-ray is hitting the specimen, and if there is a void, there is a pore, there is something, air structure inside, the X-ray will detect it. The X-ray, when it passes through a metal or when it passes through a void, it will have a different characteristics. And there is something called like a image reconstruction. So you keep on rotating this stage. So for example, I have an object. If I look at the object from this side, I will see something like that. But if I look at the object from this side, I'll see some other type of structure. So now I keep on taking this image from different viewpoints. So I get like a cluster of different structure. I can now intelligently merge those structures to reconstruct my original part. So that's what an X-ray does. It's actually a very cool device, and depending on how well you can calibrate, you can see something like 8 micron kind of defect or 8 micron kind of structure inside any metal specimen. So that means now, and again, this is one of the device actually at Penn State. So basically, this is so big, I can actually go inside it. This is almost the height of me, this particular configuration. So you can pretty much go inside it, and you can calibrate, you can put your stuff, and you can start experimenting. You should not be there when the X-ray is on, because X-ray is not good for health. So you should close the door and take proper precautions and everything. But we have it. I actually had a video, but I figured out I couldn't embed it properly. But now I'll show you the result. Some of the results I haven't still published it. So basically I removed the scales from the results. But this is what actually it does. For example, if you have a metal piece, look at that. This is a metal piece. From outside, you cannot see anything. You put X-ray, or you actually take it to X-ray computed tomography, you start to see what is actually inside. So these are some of the pores and defects and structures and everything that is inside the metal piece. It is something which is not visible to human eye, because of course, you cannot see inside a metal piece, right? But again, you subject the specimen to X-ray computed tomography and you should be able to see what is inside. So now, combining this X-ray, now our problem is solved. So basically, now if I have a testing machine, if I have I was talking about this tensile testing, right? That I can do the testing. So now if I have the testing machine inside the CT, so, there is this stage. On top of that, if I can build a machine, I can build an equipment which can do the testing inside the CT. That means now I can exactly point out how or where the specimen actually starts to fail, exactly where the specimen is failing, and what are some of the attributes of the failure, so that I can now go back and design the implant in a much better way. So that is actually the logic, and that is what I did. Again, I didn't want to show you the exact picture of the device that my students actually fabricated, primarily because we haven't published it yet. Oh boy, I am already over time. I didn't realize. So basically, now we actually made a lot of those specimens with this metal foams, and we did some ton of some analysis. And I must tell you that this experiment is actually not that trivial. It takes us almost 12 hours to test one specimen, because we have to take everything inside, calibrate, then bring everything outside. So some of our observation is that that failure always happens near the edges. So edge of the specimen always breaks fast. You have a liquid, it actually aggravates the failure process. So your failure is going to be aggravated if you have a salt water, as opposed to not having salt water or not having any salt. Then if you have more void fraction, you actually have, again, higher amount of failure. So I know the bones are porous, but I cannot make the metal foam maybe as porous like the bone, because it is going to actually fail at a faster rate. Some of the things we are pretty much trying to investigate now is how we can, even further improve the design. Basically, again, I am showing only the tensile load, but tensile load is actually a very rudimentary form of loading. Torsion is actually the more complicated ones. We also want to evaluate the effects of different material, because we printed everything with Ti-64 or the titanium alloy, but there may be other material which are actually better. And again, we want to investigate. We just investigated maybe 1 or 2 different type of electrolytes, but we want to investigate probably a range of different electrolytes and dissolved oxygen, so that we know exactly how this mechanism of failure is happening. These are some of the places which funded my research. And with that, thank you so much. I think pretty much like a chatterbox, so I appreciate. Thank you.
Thank you, Dr. Pasak. That was, and we appreciate your presentation. That was wonderful, very informative. And we are glad that you were able to show us so much. And I guess a lot of us who would not have understood those who are not from the science background also found something very interesting in this presentation. And I'm sure there are a lot of questions that some people may want to ask you. And so I'm handing over this interactive session to Ms. Pooja Tamang and Mr. Prasenjit Biswas. So Pujata Amang and Mr. Prasenjit Biswas, can you please take over and assist Dr. Pasak to answer these
Yes, ma'am.
questions?
Yes, ma'am. Thank you, Dr. Basak. We are grateful and fortunate for your time. Even though it was uneven timing, quickly I will put some questions.
Sure.
The first question is from Mr. Manav Biswas. The question is there any possibilities that human organs are also can be produced by 3D printing in future?
Oh, it is already happening. Lawrence Livermore National Lab, they actually are in the process of making artificial skin. So, there are a lot of burn victims or, especially, military when they go to the war front, there may be, situation where they sort of like, lose, skin material. So there is already that effort. And I also think there is another effort wherein, I personally also work on tissue kind of material. So basically, if you are aware, when you consume any of the tablets like drug, tablets, like normal tablets, the outer layer is typically made of like nanocellulose or cellulose kind of material. And cellulose is something like body, it's compatible to your body. So you can actually make tissues using those kind of stuff so that your recovery is going to be faster. And I think there is also an effort wherein they actually tried 3D printing a kidney. I don't know whether they have implanted it, but definitely, they tried it, and definitely it's on the horizon. Because it is already like, at least the material aspect of it has already been started. There are cases where people actually are investigating the material. What type of material do we need to print like an organ? Yes, absolutely.
Thank you. Maybe Mr. Biswas has got his answer. Another question is from Meeta Singh. The question is, in any implantation in the body, is there or will be changes in the material which are used in implants after certain periods?
I don't think I understand the question. So basically, you are implanting, or you are making an implant with, say, some material. You are asking me whether over a period of time the material would
Yes.
change.
Yes, ma'am. I think so. The question is that.
So that is what you want to avoid, basically. So that is why, how would the material composition change? The material composition would change if, suppose, your blood or the body fluids, they are interacting with the implant material, right? So that may corrode or erode, and that is how the composition would change. And that is why what we want to avoid. You do not want any reaction with the implant material, because you do not want, suppose, if it corrodes and if the extra iron goes inside your blood, that is actually not good for you, not good for anyone. So you want to avoid it. You would like to avoid it. So the answer is like, we need to minimize. We have to minimize as much as we can.
Okay, thank you, ma'am. The next question is, I'll just put 2 or 3 questions. Is it okay, ma'am?
Yeah, sure.
Okay. The next question is from Ashish Chetri. The question is there any mechanism to reduce the tensile load once the metal implants are integrated inside the body?
So basically, as I said, tensile load is actually not the critical load as such because I was told by Dr. Sanjay Shaha that there would be diverse set of people attending the webinar. I actually did not go to some of the loading which you typically see. One of the most common loading which you typically see in your body is something called a fatigue loading. So basically, it's like a cyclic loading. And that is why, during physiotherapy or during, post recovery, the doctors would probably tell you that you should not play football with your leg now, because, you shouldn't put yourself so much of like, strain in your implant, or basically you shouldn't probably try to climb Mount Everest, with your implant, because, it's going to put a lot of load on it. So yeah, there are gonna be restrictions. Nature is much more nature is the finest engineer. We are just trying to be like her, but we are not there yet. So after there are going to be restrictions in terms of what is the maximum level of activity you can potentially do.
Okay, thank you, ma'am. I'd like to put the last question. This is from Raptika Das. The question is, how these type of metallic transplant relevant with any osteophyte patients?
So basically, again, I am not a medical person. So osteo, whatever that term is, can you explain to me what is this thing?
Actually, ma'am, I just read out the question from the chat box.
Is it something related to the bone getting like weak because of the osteoporosis or something? Because as I said, I'm not a medical person. So
Yes,
I would
yes.
imagine that.
Yeah,
Okay.
ma'am. Okay then.
Yes, ma'am.
So
Ma'am,
if it is getting weak, there are cases where they put like plate, right? They put like an extra support. The way they put a plate where when your bone fractures, so there could be like an extra support which would give additional strength to the bone. Yes, that is possible.
Oh, she's saying it is related with the knee pose.
Oh yeah. Knee joint is also possible. I mean, I just showed the hip ones because I just wanted to pick up one example. But yeah, all the other types are also possible. And the design depends on the functionality. So the hip has a certain requirement. So the joint design would be, related to that kind of functional requirement. But the knee has a different type of requirement. So that design would be a bit different. But yeah, it can be done. Yes.
Thank you very much, ma'am, for your precious time. If you can kindly drop the email address of yours so that the other participant can drop the question to you, if it is okay with you, ma'am.
Oh yeah. My email ID is anyway like if you just search with my name, it is just available to everybody. So yeah, that's my email.
Okay. Now then, moving to the end, I would like to handle over this session to Dr. DC Roy, sir. Thank you. DC Roy, sir, over to you.
Dr. DC Roy? Dr. DC Roy, are you with us?
Yes, I am with him.
Okay, sir, over to you.
Hello?
Hello? Yes, we can hear you, sir.
Hello?
Yes, sir, we can hear you.
Yes, sir, you are audible, sir.
Yeah. Now, the first session may be over, so we will be joining for the second session at 5 p.m. Okay, thank you all.
I would like to thank for joining us, for giving your precious time, and I'm glad that you have been able to share with us your findings, your research work, and I'm glad that it is helping the medical people there at Penn State. And thank you once again for joining us, and to the others also, all the participants, thank you all for joining us. We will meet again at 5 p.m. Please do join us then. Thank you once again, everyone.